Welcome back, everyone. Reverse Bloom's taxonomy is a way of flipping the traditional order of learning stages so that higher order reasoning can be attempted first, and then the details and memorization follow later. In the context of artificial intelligence, this shift could influence how systems are trained, evaluated, and designed. Today, we will explore the principles behind this concept, how it contrasts with standard learning approaches, what companies and research institutions are experimenting with, and what this could mean for the future of AI. Subscribe now. Bloom's taxonomy, developed in the 1950s, has been used as a framework for classifying levels of human learning. The levels typically move upward from remembering to understanding, to applying to analyzing to evaluating and finally creating. Reverse Bloom's taxonomy proposes that in certain contexts, the order can be inverted. Instead of beginning with facts and basic recall, systems attempt high-level reasoning or creation tasks first. The process then works backward to reinforce memory and comprehension. This is counterintuitive from a traditional teaching standpoint, but may offer advantages when designing AI systems that can generalize. In its forward order, Bloom's taxonomy has long shaped lesson design in schools and universities. Teachers begin by ensuring that students can recall definitions, formulas, or vocabulary, which is the remembering stage. Once this is secure, students demonstrate understanding by explaining concepts in their own words or identifying examples. The next level is applying, where learners use the knowledge to solve problems or perform tasks. Analyzing follows, requiring them to compare, categorize, or identify patterns. Evaluating involves judging the quality of arguments or solutions. Finally, creating tasks asks students to design new projects or propose original solutions. This sequence is seen in practice when a mathematics teacher first requires memorization of equations, then applies them in sample problems, then analyzes multiple solution paths, and later asks students to design their own problem sets. The forward sequence provides a scaffolded pathway, ensuring each stage builds on the one before, and it has become a widely adopted instructional strategy across many subjects worldwide. In AI development, a reverse ordering of tasks could be applied during model training or evaluation. For example, instead of starting with rote memorization of labeled examples, an AI could be tested on novel synthesis problems. Once gaps in reasoning are revealed, the training process could target lower-level reinforcement to fill missing foundations. Researchers at MIT's Computer Science and Artificial Intelligence Laboratory have discussed the need for models to display flexible reasoning rather than just pattern recognition. A reverse approach might provide a more rigorous filter for identifying whether systems have true generalization capacity. This principle aligns with how large language models are often benchmarked. Companies such as OpenAI, Anthropic, and Google DeepMind do not only measure accuracy on memorization tasks, but also on complex reasoning tests like MMLU or Big Bench. A reverse taxonomy approach suggests going further by demanding high-level creativity or evaluation first. If the model passes those benchmarks, only then is it worth exploring its retention of basic knowledge. This resembles the idea of screening intelligence at the top end before validating details at the base level, which could save time and highlight systems capable of abstraction. One application could be in autonomous vehicles. Tesla, Waymo, and Toyota are designing cars that must evaluate complex road scenarios. Rather than only memorizing traffic rules or sign recognition first, systems could be placed into high-level decision-making simulations. For instance, deciding the safest maneuver in a sudden obstacle event requires analysis, evaluation, and creation of a new response. If the system fails, developers can trace back to whether the recognition of road elements or memory of rules was inadequate. This inversion of assessment may expose weaknesses earlier in development and prevent overconfidence. Academic research provides additional support for this method. A 2023 article in IEE Spectrum noted that focusing solely on memorization benchmarks may inflate the impression of capability. By testing high-order reasoning initially, one can identify brittle areas in a model that would not appear through factual quizzes. The University of Oxford's engineering department has experimented with reverse-order problem sets to measure whether AI students could handle advanced synthesis tasks without step-by-step prompting. Results suggested that exposing weaknesses in this way clarified where foundational reinforcement was truly needed. In robotics, Boston Dynamics and ETH Zurich have worked on machines that must adapt to unstructured environments. Traditional training teaches each step in isolation, such as lifting or balancing. A reverse taxonomy approach would instead present the robot with a high-level problem, like retrieving an object from uneven ground. Only after failing would the training emphasize the subskills like stabilizing or grasping. By approaching learning backward, developers may identify emergent strategies or shortcuts that forward training does not reveal. This could be useful for collaborative robots in industry where tasks are variable. A challenge is that reverse ordering assumes the system has enough initial capacity to attempt higher-level tasks without basic grounding. Some critics argue this may be inefficient, especially for models with limited prior training. For example, an AI language model without vocabulary knowledge cannot be expected to evaluate philosophical arguments. Yet in large-scale pre-training, as performed by OpenAI or Meta AI, models already acquire vast amounts of background data. In those cases, beginning with high-order evaluation may be viable. Researchers at Stanford University reported in Nature Machine Intelligence that pre-training provides sufficient scaffolding for reverse evaluation. Another context is education technology. Companies such as Duolingo and Coursera are embedding AI tutors that adapt to student performance. Reverse Bloom's taxonomy could be used by presenting learners with synthesis tasks at the start of a module, such as writing an essay in a new language before memorizing vocabulary lists. The AI system would then diagnose gaps and assign lower-level drills. This mirrors how human teachers sometimes use diagnostic exams. Implementing this strategy in AI tutors might accelerate mastery by forcing active use of concepts and identifying weak foundations in real time. Reverse Bloom's taxonomy also connects with reinforcement learning. In standard reinforcement learning, agents start with simple tasks and progress to harder ones. Projects at DeepMind have explored curriculum learning in reverse. Agents are placed in complex environments such as multi-step games and learn to decompose tasks backward. This can reveal innovative strategies. For example, in the StarCraft II learning environment, agents that faced full game conditions early developed unexpected tactical solutions, later reinforced with basic micro-skills. This supports the claim that starting with complexity can sometimes yield stronger generalization. In terms of evaluation frameworks, governments are beginning to adopt reverse-oriented benchmarks. The European Commission's AI Act proposals include stress testing of AI systems on high-level societal risks before checking compliance with narrower technical standards. This, in many ways, mirrors reverse Bloom's logic. In the United States, the National Institute of Standards and Technology has piloted tests where models are first exposed to adversarial reasoning problems in domains like finance or healthcare. Only after those evaluations do developers proceed with lower-level compliance checklists. This top-down strategy seeks to prevent catastrophic failures. Real-world case studies highlight the difference. Consider medical diagnosis AI from IBM Watson Health, which initially emphasized factual retrieval of medical guidelines. When tested on complex patient cases, however, gaps in reasoning appeared. Reverse ordering would have flagged those gaps earlier. In contrast, researchers at Mayo Clinic working with Google Health trained models by first exposing them to complex diagnostic scenarios. From there, they built backward to reinforce foundational recognition of symptoms. This sequence produced more reliable diagnostic recommendations, according to reports in Science Translational Medicine. The contrast shows how order matters. Another example is quantum computing research. IBM and Google are advancing quantum processors with ambitions for fault-tolerant systems. Traditional progress checks focus on error rates at the level of qubit stability. A reverse taxonomy approach would begin with high-level algorithmic performance, such as the ability to approximate chemistry simulations, and then work backward to qubit coherence. This can identify whether system-wide goals are feasible before investing heavily in refining base-level hardware. Researchers at the Max Planck Institute have argued that benchmarking quantum systems at the application level first can prevent wasted resources. Reverse Bloom's taxonomy can also be linked with explainable AI. A high-order requirement is to evaluate and critique model reasoning. If AI is asked to justify its decisions first, failures in explanation may point to missing understanding at lower levels. DARPA's explainable AI program has pursued such goals. Models must explain outputs before proving factual accuracy. This top-down demand aligns with reverse ordering and may lead to more trustworthy systems. By contrast, standard approaches test factual recall before explanation, which may obscure underlying weaknesses in reasoning chains. The near future could see companies adopt this methodology more widely. In 2026, it is expected that many AI benchmarks will integrate creation and evaluation tasks at the start. For instance, Anthropic has announced plans for safety evaluations that begin with open-ended reasoning stress tests. Only if models pass will lower-level factual reliability be assessed. This shift reflects growing awareness that factual recall is not sufficient to guarantee safe deployment. If companies adopt this systematically, reverse ordering could become a new standard for assessing advanced AI systems. In the medium term, the implications extend to workforce training. Corporations like Siemens and General Electric, for instance, rely on AI systems for industrial optimization. If reverse taxonomy methods are applied, these systems might be tested first on strategic planning scenarios, such as balancing energy demand across grids, before being drilled on component-level maintenance. This could allow earlier identification of whether AI tools are actually suitable for integration. It may also change hiring practices, where human employees are evaluated on problem-solving before factual quizzes, with AI systems serving as both tutors and evaluators. There are, of course, limitations. Reverse ordering may cause overestimation if systems appear to succeed at high-order tasks by chance or pattern mimicry. For example, language models might generate convincing but shallow answers on abstract questions while lacking underlying knowledge. Researchers at Carnegie Mellon University caution that reverse benchmarks must include careful validity checks. Another issue is computational cost. Running high-level simulations first can be more expensive than starting with smaller unit tests. Companies must balance efficiency against the benefits of exposing weaknesses earlier. These trade-offs remain subjects of debate in academic journals like AI and Society. Looking further ahead, long-term impacts could reshape AI governance. If global standards adopt reverse evaluation, certification processes may require demonstration of reasoning capacity before factual reliability. International organizations such as the OECD and UNESCO have considered frameworks that prioritize societal-level evaluations. This could influence how future AI is licensed for use in healthcare, defense, or education. By 2030, it may be routine for AI systems to face top-down audits before deployment. This would align with reverse taxonomy and alter the culture of AI development across both industry and academia. Reverse Bloom's taxonomy therefore represents more than just a teaching curiosity. It could change the order in which we test and train intelligent systems. By beginning with evaluation, analysis, and creation tasks, AI developers can expose hidden weaknesses earlier and guide reinforcement of foundations more effectively. Companies like Google, IBM, Tesla, and Boston Dynamics provide case studies of how such principles may apply in practice. Universities and government agencies are also experimenting with top-down benchmarks. While challenges remain, the potential benefits for reliability, safety, and efficiency are significant. Thank you very much for watching. Please like and subscribe.